Hey everybody, today we're talking about inverse trigonometric functions. So right away, right off the bat, when we talk about trying to invert trigonometric functions, we have a big problem. They aren't one-to-one. For example, here's sine of x. It doesn't pass the horizontal line test. Any horizontal line I draw is going to intersect the graph in many, many places. So if we want to get an inverse for something like this, we're going to need to restrict the domain of the function. Like so. I'm going to say that sine has to be between negative pi over 2 and pi over 2. Now I have a one-to-one function, and I've also captured the entire range. All the y values between negative 1 and 1 are included here. So with that intuition in place, we have a definition to make. Y equals sine inverse of x means x equals sine y, and y is in the interval from negative pi over 2 to pi over 2, including the endpoints. When you read sine inverse of x, the words you should be thinking are the angle whose sine is x. So the inverse sine in particular is an angle. With that intuition in mind, we can draw pictures. When you see sine inverse of x, you can think about an angle in a right triangle whose opposite over hypotenuse has a ratio of x over 1, or x. That triangle specifically, though, of course, only makes sense when the inverse sine is positive, when that angle is positive. If it's negative, you have to draw it on a unit circle. One other tiny bit of notation, sometimes instead of sine inverse, we say arcsine. That's pretty common as well. You'll hear me switch back and forth as I speak. Let's have an example. Let's compute the inverse sine of the square root of 3 over 2. We interpret that as the angle whose sine is root 3 over 2. And the angle has to be between negative pi over 2 and positive pi over 2. So we draw a triangle. The opposite over the hypotenuse is root 3 over 2. We need to find that angle. This is a familiar triangle. So 30, 60, 90 right triangle. That angle has to be 30 degrees or pi over 6. The other 5 inverse trig functions are defined in a very similar fashion. Unfortunately, we can't just use that same domain restriction for all of them, and pictures make this clear. So here's cosine. Cosine is not one-to-one even on negative pi over 2 comma pi over 2. We need a different domain restriction. Tangent, it's maybe even worse. It's not even defined at those endpoints, negative pi over 2 and pi over 2. So we need different domain restrictions really for all of them. These pictures are helpful because they do suggest to us what some good restrictions might be. Here are the definitions. Y equals inverse cosine of x means that x equals cosine of y, and y is on the interval 0 comma pi, closed interval. And y equals tan inverse of x means that x equals tan of y, and y is between negative pi over 2 and pi over 2, this time leaving out the endpoints to respect those vertical asymptotes. The other 3 inverse trig functions get defined in a similar manner. They get used less frequently. The 2 that come up most often, by the way, are arctangent and arcsine. Here I'm covering inverse cosine as well. Let's do one more computational example. The arctangent of negative 1. We need an angle, call it theta, between negative pi over 2 and pi over 2, whose tangent is negative 1. Let's try and draw this on a unit circle. It's going to have to be in the fourth quadrant because the tangent is going to be negative, and it can only be in the first or fourth quadrant by definition. So actually, what is that angle? Well, we remember that tangent means the y value over the x value, sort of an opposite over adjacent. So if it's going to be negative 1, we recognize that angle is going to have to be pi over 4 in absolute value. Since it's below the x-axis, we're going to say negative pi over 4. Altogether, arctangent of negative 1 is negative pi over 4. The domains of the inverse trig functions are the ranges of the corresponding functions. So, for example, the domain of the arcsine, sine inverse, is from negative 1 to 1. There is no angle whose sine is bigger than 1 or less than negative 1. Similarly, the domain of the inverse cosine is from negative 1 to 1, and the domain of the inverse tangent is from negative infinity to infinity. Notice that the domain of the original trig function is not exactly the range of the inverse trig function, simply because we had to restrict those domains in order to do the inverses. All inverse functions obey cancellation properties, but with inverse trig functions you have to be a little bit careful because of the restriction that we put on the domain of the trig functions we're inverting. Let's see what I mean. The sine of the sine inverse of x is just x for all x in the domain. That one's straightforward. But things get a little tricky on the other one. Sine inverse of sine of x is x only when x is between negative pi over 2 and pi over 2. Remember that the arcsine is always giving back a value in that range. So if you start by plugging in a value for x that's outside of that range, take the sine of it and then take the arcsine of it, you're going to get something different back. Couple of examples. The sine of the sine inverse of 1/2 is going to be 1/2. That's the top case there, the more simple one. In words, the sine of an angle whose sine is 1/2 is 1/2. Makes sense, right? What about this one? Sine inverse of the sine of 3 pi over 4. So this one is going to be in the bottom case, and in particular, the number that we're plugging in inside is not between negative pi over 2 and pi over 2. So we're not going to get the same thing back. The sine of 3 pi over 4 is negative root 2 over 2. This is an angle in the second quadrant whose reference angle is 45 degrees, pi over 4. And the arcsine of negative root 2 over 2 is negative pi over 4. So how do we read this in words, this initial problem in words? The angle in quadrant 1 or 4 that has the same sign as 3 pi over 4 is negative pi over 4. Let's do one last problem. It's important to remember that an inverse trig function represents an angle, as this problem illustrates. Let's find the cosine of the arctangent of 3/4. This has a very natural picture. Let's draw arctangent of 3/4. We need an opposite of 3 and an adjacent of 4, like so. I've also labeled the angle, tan inverse of 3/4. I want the cosine of that angle, adjacent over hypotenuse. So I use the Pythagorean theorem to compute the length of the hypotenuse. In this case, 5. It's a 3, 4, 5 right triangle. So the cosine is going to be 4/5. Overall, cosine of tan inverse of 3/4 is 4/5.